Let's do the exercise 7.18. Let's start reading the exercise description. Consider the process model in figure 7.17, which is given here. This model captures a simplified process for handling mortgage applications. There are two checks involved. CT1 deals with a check of the financial coverage of the mortgage application, and the second check, CT2, concerns the verification of the property that is to be mortgaged. If the result of both checks is positive, so CT1 and CT2, the application is accepted. So if both are positive, we get to task C, AC. On average, after the execution of a task CT1, 20% of all applications are rejected. Meanwhile, task CT2 leads to 30% of further rejections. So 20% are rejected from CT1 and CT2 leads to further 30% rejections. If either of the checks has an unsatisfactory result, the application is rejected, task AW. The arrival process is Poisson, with an average arrival of 5 cases per hour during business hours. For each task, exactly one dedicated resource is available. The processing time of every task follows an exponential distribution. The mean processing times for tasks CT1, CT2, AC, and AW are respectively 5, 4, 3, and 3 minutes. So 5 cases per hour, processing time 5, 4, 3, and 3 minutes respectively for each task. The wage of each resource is 20 euros per hour. Not sure if we're going to use this here. Business hours are from Monday to Friday, from 9 to 5 p.m., which gives us 8 hours of business hours. Resources are only available during these hours. Determine the resource utilization of each resource, the average cycle time of the process, the cycle time efficiency of the process, and the average number of mortgage applications that are being handled at any given point in time. For this exercise, it might be convenient to use a combination of process simulation, Little's law, and flow analysis. All right. So, to determine the resource utilization, we need the arrival rate and the capacity, because resource utilization is the ratio between arrival rate and capacity. The arrival rate, as we saw, is how many cases arrive at the activity on average per hour. These we already have in our spreadsheet, as you can see here. We need to add two other columns here then. Let me just add the symbols here. We need to add the capacity, which is the rate at which you can generate process cases. In other words, capacity gives you per time unit how many cases you can produce. And the resource utilization itself, which expresses how busy the resource is while carrying out the cases. The calculations for capacity and utilization are straightforward. What is important is that they must be compared using the same time unit. Since we used hours for the arrival rate, we must determine the capacity per hour as well. We can determine the capacity, in other words, the number of cases a resource can handle per hour using the processing times. So considering it takes 5 minutes on average to carry out CT1, the capacity of processing cases for CT1 is 1 hour. In other words, it's 60 minutes divided by the CT1 processing time, which is 5 minutes. This leads us to CT1's capacity equals to 12 cases per hour. And based on the same logic, we find the capacity of the other activities, which lead us to these, and the Google spreadsheet helps us fulfilling this, but as you may see, the logic is the same. We have 60 divided by the processing time of each activity. Now we can easily calculate the resource utilization, which, as mentioned before, is a ratio between arrival rate and capacity. So we have arrival rate divided by capacity. And now we have the answer to the first question. We can also see that the resource utilization for each of the resources is below 1. And this is important. It shows that the system is stable and the formulae like the M1 and Little's law are applicable at all. So the answer is C column, utilization. Let's move to the next question, where we need to determine the average cycle time of the process. If all the activities were all executed once, one after the other, then that would be easy. We would simply add the average time it takes to execute each activity, and that would give us the answer. But when we look at this process model that we are given by the exercise, we see that this is not the case, right? therefore, we will need to identify the probability of each activity that is carried out, because the average cycle time is a contribution from each activity's cycle time to the average cycle time. And it is very important to remember the average cycle time is a contribution from each of the activity cycle time to the average cycle time. Okay, so let's first find out the probabilities of each activity to happen, and we're gonna need to add another column here. And to do so, the reasoning is similar to the one we did to calculate the arrival rates. I hope you remember. In this case, the probability for any case that to be served, the probability for any case to be served by CT1 is 100%. So we have the probability of CT1 equals to 1. The probability of any case to be served by CT2 is 80%. So CT2 probability is 0.8, and so on. The probability of AC is 70% from 80%. So it is 70% from 80%. And the probability of any case to be served by AW is 0.2% from 100%. It's 0.2 plus 30% from 80%. So it is 0.2 plus 30% from 80%. And one thing that is worth mentioning here is that the sum of the probabilities of AC and AW to happen is 1. Which means that 100% of the cases will be served in this process either by finishing via AC or via AW. And as you can see in the model, that is correct, right? Now, let's calculate the system time for each activity. The system time is the concept from queuing theory that we can use to determine the average cycle time. To calculate the system time, and we're going to need to add another column here, we learned the formula W equals to wait time, that we also called WQ, plus 1 divided by resource utilization. Right? Which means that we need to first calculate the wait time. And to calculate the wait time, we learned the formula WQ equals to instances in queue, LQ, divided by arrival rate. which means, again, that we need to first calculate the number of instances in the queue. And to calculate LQ, the number of instances in the queue, we learned the formula LQ equals to resource utilization squared divided by 1 minus resource utilization. Let me just take this out to make it a bit more readable. And to calculate the instances in queue, we need the resource utilization, which we already have. So let's start calculating LQ. And to do so, we simply apply the formula resource utilization times resource utilization divided by 1 minus resource utilization. Right? And we need to apply this for each of the activities. Now we can apply the wait time. We can calculate the wait time, sorry. And to do so, again, we simply apply the formula LQ divided by arrival rate. And now we can calculate the system time, which is the wait time plus 1 divided by the capacity. What we now have is the system time for each of the activities. This is exactly the time it takes for a case to go through an activity. We can use that time to determine the average cycle time of the whole process. Okay? So, let us determine how much cycle time each of the activities contributes. It is the product of its own system time times the probability it is actually executed. So let's add another column here. And we will have the system time times the probability it is actually executed. Okay. If you find this difficult, think of it as follows. If an activity is only executed for half of the cases, it only adds 50% of its system time to the cycle time of the average case. So in the end, we can calculate the average case considering the system times and the probabilities, which will lead us to approximately, let's see, let me put this here. Zero point 273 approximately hours, which is roughly 16.372 minutes. And with this, we have our answer to question B. Nice, right? In simple solutions for this exercise, you may notice some different formulas, and some of you may ask where these formulas came from. These formulas were derived from the formulas available in the course book. And you do not need to derive these formulas yourself. Next, I will show you how these formulas were derived, and also I will show you that the results will be the same as shown in a few minutes ago. So you can pause the video and give a look by yourself, but it's quite straightforward. We use the resource utilization, alpha divided by lambda, divided by mu, and this is just the same as we can also write this as lambda equals to rho times mu. And we explore this here. So for example, the wait time is the instances in queue divided by the arrival rate. So we open the instances in queue, we do some basic mathematics, and using this formula also we replace things, and we do the same for system time. So for example, let's get this formula for system time. 1 divided by capacity minus arrival rate. System time. W equals to 1 divided by capacity minus arrival rate. If we calculate this, 1 divided by capacity minus arrival rate, we should get exactly the same results as we got here. And it seems that we do, right? We actually do. So again, pause the video, copy this, give a look, try to understand the transformations and the derivations made. And let's move to the next question. To answer question C, the cycle time efficiency of the process, we need the theoretical cycle time, also called TCT, and the cycle time, the CT. We know that the cycle time efficiency of the process is the ratio between the theoretical cycle time and the average cycle time. And we already have the latter. So let's calculate the former. Let's add another column here. So the former is the average time it would take to carry out this case if no time at all would be wasted on queuing. To determine this figure, we will reuse the probabilities and have for each of the activity, we will reuse the probabilities that we have for each activities and multiply it with the processing time of the activity. This will result in, so we're going to have theoretical cycle time equals to .2 minutes, right? 11.2 minutes. Let me do the following. I will put this here, and I will leave here to the CTE, to our answer for this question. So to find the CTE, we have the CTC divided by the CT, and we really to pay attention that we need to use the same time unit. So we are using 11.2 minutes, we need to use the 16.372 approximately minutes, and we're going to get to 0.68, which is equals to 68.41%. So this shows us that quite some time in the process is spent on queuing. As our textbook states, the closest to 100% CTE is, the less room for improving the cycle time we have, unless relatively radical changes are introduced in the process. So finally, let's answer question D. To answer question D, we will determine the average number of mortgage applications that are being handled at any given point in time. And the average number of mortgage applications is exactly our number of instances in the system. We can calculate this via Little's law, which is the arrival rate times the average cycle time. So we also need to keep in mind here, while doing this calculation, the time units we're using. In other words, if we use the arrival rate in hours, we also need to use the result in hours from the average cycle time. And if we use the arrival rate in minutes, we should also use the result in minutes from the average cycle time. In both cases, we will get to the same result in the end. So here I will use the arrival rate in hours which was given for us in the beginning of the exercise, 5 cases per hour, times our average cycle time in hours. So the number of mortgage applications that are being handled at any given point in time is approximately 1.364. That's it.